how do humans make sense of mountains of data? Well, more often than not, it's with the help of a good chart or a graph, right?
Exactly. They take these dense numbers
Yeah.
and just turn them into clear insights, making patterns pop out almost instantly.
But here's the big question. What about artificial intelligence? If charts help us understand, can they help AI understand data better too? Today, we're taking a deep dive into precisely that question. We're guided by a really groundbreaking new research paper from a team from Harvard University and Google Research.
Yeah, it's fascinating stuff.
They ran some incredibly detailed experiments with leading AI models to see if visualizations actually improve their ability to, analyze data.
So our mission for you today is to unpack their findings. We want to reveal not just what the AI models did, but crucially, why it matters. Why it matters for how we design AI systems.
Right.
And perhaps even how we think about our own visual processing of information. You should get ready for some serious aha moments here.
Okay, let's unpack this then. The core question here is whether these large vision language models, or LVLMs,
Yep.
these powerful AI systems like GPT 4.1 and Claude 3.5 that many of us are interacting with regularly, do they truly benefit from seeing charts and graphs when they're analyzing data sets?
And that's such a crucial question right now. Because while LVLMs excel at so many tasks, they can, surprisingly, kind of struggle with unfamiliar data distributions. Yet they're increasingly being used for complex data and visual analysis. They're even acting as agents,
Meaning they're trusted to complete tasks on their own.
Exactly. Autonomously. So improving their data analysis skills is absolutely critical, whether they're working alone or partnering with humans.
Okay, so to really put this to the test, the researchers designed a pretty impressive experiment. We're talking 12,000 trials.
Wow.
Across two prominent LVLMs, OpenAI's GPT 4.1 and Anthropic's Claude 3.5 Sonnet. They used the latest versions available when they did the study. And they focused on 3 common data analysis tasks. Crucially, they used synthetically generated data. Why was that so important?
Generating data synthetically was key.
Ugh.
It let them avoid any contamination from real-world biases and allowed them to precisely control every parameter.
Makes sense.
And for each of those 3 tasks, they meticulously tested 5 different input conditions. First, data only, just the raw numerical data set.
Okay.
Second, data in blank. So the raw data plus an all-white blank image. This is a control, to see if just any visual input made a difference.
Clever.
Third, data in raw data, accompanied by a deliberately misleading visualization.
Ooh, okay.
Fourth, data in different attack.
Correct.
The raw data with an accurate visualization. And finally, fifth, correct only. Just the accurate visualization, no raw data at all.
Got it. And the overarching goal was pretty simple, right? To see if these accurate visualizations, mostly standard matplotlib scatter plots, could truly help these models describe data sets more precisely, more accurately.
Exactly. Does seeing the picture help?
So, let's dive into the first task, detecting clusters. You can imagine trying to identify how many distinct groups of data points exist within a larger data set. They use data sets with 120 points, evenly distributed among 2 to 5 cluster centers. And the challenge increased with more clusters, making the distinctions more subtle.
And the findings here, they were remarkably clear. Providing accurate data visualizations significantly improved both GPT and Claude's ability to correctly identify the number of clusters.
Really?
Yeah. And this performance boost was directly attributable to the models recognizing the clusters visually, because the blank or misleading visuals, they offered no improvement over just the raw data.
So it really showed the power of actually seeing the pattern.
Absolutely. It really did.
Now, what really jumped out at the researchers, apparently, was just how profound the visualization's benefit became when the data sets grew more subtle, when precise cluster identification was really needed.
Yeah.
For data sets with 4 or 5 clusters, GPT became at least 2.3 times more accurate. And Claude was 1.7 times more accurate with the correct plot compared to when they didn't have it.
That's a huge difference. And that performance gap, it was driven by a sharp decline in accuracy for the data-only conditions, especially when moving from 2 to 3 clusters. It sort of indicates that relying solely on raw numerical input can be quite brittle for these LVLMs when the patterns aren't immediately obvious.
Right. It's like they can't see the shape in the numbers alone sometimes.
Precisely. And interestingly, when the models did fail, they almost always underestimated the number of clusters.
Now, here's where things get genuinely maybe a bit unsettling. What about the data and wrong condition? The one where the misleading visual showed only one cluster.
Oh, yeah. That consistently led to the worst performance. Both models tended to just output 2 clusters, regardless of the true number.
Regardless.
Almost as if they were just fixated on that misleading image, yeah. But what's even more concerning is this. GPT and Claude only mentioned a discrepancy between the raw data and the misleading visual in 7 out of 800 trials.
Only 7 out of 800.
Yeah. It suggests a pretty significant blind spot, doesn't it? They might just silently fail when given conflicting information. They seem to prioritize the visual over the underlying data without even flagging it.
That's a profound vulnerability to consider, isn't it? I mean, if these models can just accept a misleading visual and largely ignore contradictory data without a warning, how do we know when to truly trust their autonomous analysis?
It absolutely highlights a crucial area for future development. The paper sort of implies we need better mechanisms for AI to, express uncertainty or flag inconsistencies.
Rather than just giving an answer.
Exactly. Rather than just silently producing an answer based on potentially flawed input. It's a huge frontier.
All right, let's move on to the second task. Spotting parabolic trends. Curves in data.
Right.
Here, the researchers challenged the models to identify these curves. Subtlety, in this case, basically meant how hard it was to visually spot the curve. Like imagine trying to see a parabola with just a few scattered dots versus a clear arc of many points.
Mm-hmm. Fewer points beyond the parabola's vertex made the trend much less obvious.
And the results?
Well, once again, Claude and GPT performed best with an accurate plot, especially as those datasets became more subtle.
Okay.
And strikingly, the data and wrong condition, remember, where the misleading visual showed a linear best fit instead of a curve.
Right, a straight line.
That consistently induced the worst performance. Across all subtlety levels, this misleading visual cut, the success counts by more than half compared to any other condition.
Wow, more than half. So what does this tell us about the influence visualization has on AI? It seems like including a misleading graphic didn't just confuse the AI.
No, of course.
It effectively overrode the model's interpretation and discussion of the raw data itself.
That's right. The frequency of broad trend descriptors like nonlinear or curved, it decreased up to 8-fold when a misleading visual was present. They just stopped talking about the curve they might have seen in the data.
Incredible.
There were some really interesting nuances, though. For the most subtle parabolic datasets, the ones with only 3 points beyond the vertex.
Yeah. The really hard ones.
Claude had virtually no meaningful performance. Even with a correct visual, it sometimes completely misinterpreted it. It started mentioning things like logarithmic, logistic, or sigmoid in like 91% of its responses for those cases.
So it saw a curve, but not the right kind of curve.
Kind of. Or it got confused. And here's a genuinely surprising twist for you. For those very subtle parabolic datasets, the correct only visualization condition,
Yeah.
just the picture,
Yeah.
it actually outperformed all the others.
Outperformed even having the data and the picture.
Yes. For instance, when Claude was presented with 5 points beyond a parabola's vertex, including the raw data alongside the correct scatter plot, actually reduced its performance by a factor of 3.7.
Get out. Reduced it.
Reduced it, yeah. GPT showed a similar, albeit smaller, effect for the 3-point data sets.
Yeah.
It really challenges our assumption that more data is always better for AI,
It really does. It suggests that sometimes a clean visual summary can be profoundly more insightful on its own, maybe even less confusing than having the raw numbers there too.
It absolutely does. It
Yeah.
makes you wonder if, maybe in certain complex visual pattern recognition tasks, the raw data actually adds noise. Or perhaps clarity for the AI. Or maybe the model's visual processing pathway is sometimes just more efficient than its numerical one.
Fascinating. Okay, finally, the third task, outlier detection. Finding that one specific anomalous point in otherwise linear datasets.
The odd one out.
Exactly.
So, as in the previous tasks, visualization helped both models identify the correct outlier, and its benefit increased with task subtlety, just like before.
Okay, consistent there.
And once again, the data and wrong condition consistently produce worse results than other conditions. No surprise there anymore, maybe.
Right, that seems to be a running theme. But
Okay.
there was a twist here, wasn't there?
There was. This is the fascinating counterpoint. Unlike the previous two settings, for outlier detection, both GPT and Claude generally performed comparably or even better when provided with both the dataset and the correct plot,
Ah.
compared to only getting the correct plot.
So for finding outliers, having the raw data and the visual was the sweet spot. Why might that be?
Well, this trend likely relates to the nature of the task itself. Outlier detection often requires retrieving and analyzing specific data values.
Like the coordinates of that weird point?
Exactly. Rather than just recognizing a general feature involving multiple data points like clustering or the entire dataset shape like the parabolic trend, the raw data provides that precise detail, which is useful alongside the visual cue pointing you to it.
That makes a lot of sense. Okay, so stepping back from these specific tasks, what broader patterns did the researchers identify across all these thousands of experiments?
Well, one interesting observation was just the difference in response length. On average, Claude's responses were about 288 tokens long. GPT's were much lengthier, 884 tokens on average.
Big difference.
Yeah. And without an accurate visual, GPT often just outputted the entire data table before starting its analysis, which is, a lot of text.
Just dumped the data.
Pretty much. However, it's worth noting that GPT 4.1 generally matched and sometimes significantly exceeded Claude 3.5's performance across all the settings, despite being more verbose.
Okay. And crucially, what happened when they got only the visual?
Well, when provided with only the visual, both models generated the shortest, most concise responses. They were highly focused on the salient dataset features.
It was almost like the visual helped them get straight to the point.
Exactly. In contrast, when given only the raw data, the models often computed summary statistics in their responses, things like mean, median, standard deviation.
Oh, okay.
Those summary statistic terms appeared 2 times more often in GPT responses and up to 10 times more often in Claude responses when given data alone compared to visuals alone.
Wow.
So that tells us a lot about how the input format can really influence what kind of information the AI prioritizes or, chooses to discuss. Visuals seem to drive qualitative pattern recognition.
Seeing the shape.
Right. While raw data prompts more quantitative summaries, calculating things.
So what's the sort of big picture here? What does this all mean?
Well, the research provides pretty clear evidence, I think, that visualization can significantly help AI systems understand data, especially as that data becomes more subtle or complex.
And this isn't just a minor tweak, is it? It feels like it opens up truly exciting avenues of research at the intersection of visualization and AI.
It really does. And this paper is presented very much as a proof of concept. It raises these tantalizing questions that go far beyond its initial scope.
Like what?
Well, for example, how do different graphical variations, all those countless choices that go into chart design, from colors to axis labels to chart types, how do they affect these results for AI? Is there an entire parallel field of visualization studies needed, but specifically tailored for AI systems?
A whole viz for AI field.
Maybe. And this leads to a really provocative thought for you, the listener, to mull over.
Okay.
If the same graphical ideas, the same chart designs, turn out to be consistently best for both humans and AI, could interpreting how AI systems process visuals actually shed new light on human psychology, on how we process information visually?
Oh, using AI to understand ourselves better.
Potentially. Or the alternative. If there are systematic differences, do we need to build up a whole new field of AI-oriented visualization where charts are designed specifically for AI audiences, not human ones?
Charts just for the machines.
Yeah. And the ability to prompt these AI models thousands of times relatively cheaply. It could potentially allow for incredibly personalized visualization design in the future.
Personalized for the task or even for the specific AI model?
Both, perhaps. It opens up really profound implications for how humans, AI, and human AI workflows interact down the line. There's always more to learn, isn't there?
Always.
And these findings really, they feel like just the beginning of that exploration.